Hey everyone, it's Shane. Now back in May, Red Hat released the State of Kubernetes Security report for 2022. Now if you haven't come across this document before, it basically analyzes emerging trends in containers, Kubernetes, and cloud-native security, and how organizations are addressing security challenges and protecting their cloud-native applications. So I'll leave a link in the description of this video, and you can see some of the key findings here from the 2022 report. Now these are collated from surveys across 300 DevOps and security leaders from around the world, and they represent large enterprises, small to medium-sized businesses, and smaller organizations also. Now one of the findings I think is really interesting is that over half of organizations worry most about securing workloads at the runtime phase. And I wanted to kind of explore a little bit more about why I think that is and how we can support those organizations with the runtime phase of cloud-native security. Now, I think that organizations are particularly worried about that runtime phase of security because it represents a change in how they've traditionally managed security for applications. Now, this is a common pattern that organizations use to protect virtual machines. They typically deploy agents onto workloads or servers to provide observability. So they might deploy, say, a Nessus agent to provide insights into vulnerabilities on that node. Or they might deploy something like CrowdStrike to support detecting anomalies and anomalous behaviors. So they deploy agents typically to provide observability. And then organizations will typically provision access to be able to make changes on that node, to be able to remediate it back to a security baseline, or to perform some other kind of incident response or investigation enrichment. So access and agents is a really common pattern for virtual machine security. It gets a bit interesting applying that pattern to containers and Kubernetes. Now, typically for containers, we don't have agents running inside the container. And that's for a couple of reasons. It makes it more difficult to provide consistency. So if we're looking at trying to deploy workloads from development into production, we need to have that same agent-based infrastructure in all of those environments. And it also restricts portability, because suddenly now I can only deploy those workloads in environments where I have that infrastructure available to support that agent. We also typically don't provision access into containers. And this is because it destroys consistency. And again, I should be able to deploy that workload from development all the way into production. And if I have access into those containers, potentially have files changing from under workloads or configuration changing, it's going to make that consistency much more difficult. So we don't have access and we don't have agents. How can we support securing these workloads at runtime? So one of the ways that organizations can support these environments is through a Kubernetes-native approach to security. Now what I'm going to look at today is a demonstration of Kubernetes-native runtime security. What I'm going to show in this demonstration is an attacker attempting to exploit a vulnerable container application. We're going to detect that behavior, in this case using a cloud-native security platform called Red Hat Advanced Cluster Security for Kubernetes. And then once we've detected that behavior, we're going to take some action. We're going to perform some incident response using the Kubernetes API. So we're going to detect that suspicious behavior, and then we're going to immediately take some action using the Kubernetes API. Now the vulnerability that I've used for this demonstration is Log4Shell, and it's a 0-day vulnerability present in Log4j, a popular Java logging framework. Now I've chosen Log4Shell for this demonstration for a couple of reasons. The first is that it's ubiquitous across Java enterprise environments, and a lot of organizations have spent a lot of time and resources trying to mitigate this vulnerability. So we want to look at today some runtime security approaches that we can use to mitigate this risk. It's also very simple to exploit, and you'll see that during the demonstration. So I'm going to start by identifying that vulnerable application. Now this is my Red Hat Advanced Cluster Security platform, and I'm going to start with this vulnerability management section. Now here I've got a dashboard showing me all of the vulnerabilities across the container images known to Red Hat Advanced Cluster Security. Now what I'm going to do is have a look at the images that the platform has scanned, and we're going to look for, in this case, a particular CVE. So we're going to do a search in here for CVE 44228. Now this is the one of the log4shell CVE identifiers. Now what I can see is that I have one application or one container image that is vulnerable to log4shell. And I can see that right at the top of the list. I've got this critical severity CVE with a CVSS score of 10. So I know I need to do something about this vulnerability. What I can also see here is that I have one deployment that the CVE is matched against. So this means that somewhere inside my environment, my Kubernetes platforms, I have a vulnerable application. Now in this case, I can see that that application is matched with this log4shell app deployment. It's in my production cluster and in the DevOps namespace. So this is that application that is vulnerable. It's in the DevOps namespace, in my production cluster, and it's my log4shell app deployment. So I can see I've just got one pod currently running, and it's actually exposed at this route. So let's see firstly how we can exploit this container application, this vulnerable cloud-native application. Now what I have set up on this host is some simulated attacker-controlled infrastructure. So what we're going to do is set up a TCP socket. We're going to exploit our log4shell vulnerable application and force it to connect back to this infrastructure and get a shell inside that container. So let's set up our socket. Now exploiting log4shell is, as I mentioned, is trivial once I have this infrastructure in place. So what I'm going to do is simply make a request to our vulnerable application. I'm going to force it to log this XAPI version header, and that contains our, in this case, base64 encoded commands we're going to use to set up that shell session. So let's run that command. And we'll see that we get a shell, in this case, inside that container application. Now I can see here I'm actually the root user, so this application hasn't been correctly configured. But I can also see some additional configuration inside here. For example, I can see all of the application files, for example. I could also potentially grab the service account token that's been mounted inside this pod and potentially make some requests against the Kubernetes API from this compromised workload. So not a great situation for this application. What we're going to look at next is how we can detect this type of activity and then respond to it in a Kubernetes native way. So I'm back in my Advanced Cluster Security platform. And what I'm going to look at this time is some of the policies available inside the platform. Now, all of these policies are available out of the box, and they apply to the build, deploy, and runtime lifecycles. So today we're going to look at those runtime container security lifecycles. Now you can see right up the top here, I have a policy shell spawned by a Java application. Now what we're going to do is use this policy to detect and enforce this type of anomalous behavior from applications. So what this policy is going to do is it's going to detect shell as a sub-process of a Java application. Now inside this organization, that's almost certainly going to be an indicator of compromise. Because in this organization, applications are developed that don't shell out, that don't create those shell processes as a sub-process of Java. And so we're going to immediately know that this is malicious activity that we need to further investigate and take some action to respond to. You can also see here we've got some MITRE ATT&CK alignment. And you can see right at the bottom that policy criteria. So we mentioned we're looking for processes that look like shell as a sub-process of a Java application. So what we're going to do is enable that policy, and we'll look at setting up that exploit again. So I'll set up my socket and we'll exploit that application. Now this time we see some different behavior. So I can still enter some commands, but I'm not getting anything back from, in this case, the exploited application. Now we can see the reason for that inside this violations section. So what I can see here is I've got a shell spawned by Java application for my log4shell app in that production cluster and the DevOps namespace. So if I have a closer look in there, we can see those decoded base64 commands that I tried to pass into the application. We can see the time that this activity has occurred. And in this case, we can see that we've been able to take some action. In this case, we detected that activity and we killed the pod using the Kubernetes API. So in this case, we detected that activity and immediately took some action using the Kubernetes API, in this case to wipe out any and all potentially attacker and controlled processes. I've also got some more information about that deployment here. That was, in this case, where we detected that anomalous activity, and we can see the policy that was violated. So what we saw in that really quick demonstration is how we can start to take a Kubernetes-native approach to runtime security. In this case, we looked at exploiting a vulnerable container application. We looked at how we can detect some of that suspicious behavior from applications. And we also took some action or performed some incident response in this case. We're able to detect that behavior and in this case, kill that pod using the Kubernetes API and then record both that activity and the action that we took inside Red Hat Advanced Cluster Security for Kubernetes. So I hope this has been useful for you today, and I'll post the link to that State of Kubernetes Security report in the video description. Thanks.